The dictionary defines gravity as the pull towards the center of the earth. And if we ask different people, that's probably the most common definition we would hear. Yes, many textbooks and dictionaries have given that as their definition. Too bad it's incomplete. Today, we'll find out the real definition of gravity and some of its characteristics as we explore gravity. It's silly to think that gravity is simply the pull towards the center of the earth. A man on the moon would not go along with that. He would be experiencing a pull towards the center of the moon. Actually, gravity is an attractive force that acts between any two objects. There is an attractive force between you and your books, or you and your desk. The greater the mass of an object, the greater its gravitational attraction. So, because the Earth is the most massive object close to us, its gravity has the greatest influence on us and objects in our world. If we drop something, it falls towards the center of the Earth. The ground gets in the way and we have a mess. So, on our planet, it does appear that gravity is the pull towards the center of the Earth. But we must remember that all objects have gravity. The more mass the object has, the greater gravity will affect it. Mass and weight are not the same thing. Weight is a measure of the gravitational attraction of an object. On the moon, the gravitational attraction is much less than on Earth. The moon has less mass than the Earth and therefore has only 1/6 the gravity. That's why this lunar rover bounces around so easily on the surface of the moon. Astronauts on the moon would weigh less than on the Earth, and all their supplies and the lunar rover would weigh less. If an astronaut weighed 180 pounds on Earth, he would only weigh 30 pounds on the moon. He didn't shrink and change size. The pull of gravity is simply less, so he weighs less. His mass remains the same. That's because mass is not the same as weight. Mass is not a measure of gravitational attraction. It is often defined as the amount of matter in an object. Scientists like to think of mass as the measure of an object's resistance to motion. Either getting an object moving or slowing it down, the greater the mass, the harder it is to speed up or slow down the object. When we weigh ourselves, we use a spring scale. A spring inside the scale is stretched. It tells us how hard gravity is pulling down on us. Our weight is a measure of the gravitational pull on our body. To measure an object's mass, we use a balance scale and a set of weights. We can measure the mass of this fruit and then take it to the moon. The mass would be the same because the change in gravitational attraction will have the same effect on the massing weights as the fruit. Weight and mass are not the same thing. Back on Earth, let's turn our attention to falling objects. For centuries, early scientists struggled to explain why objects fall towards the Earth. People could see that objects fell, but no one could explain how or why. It wasn't until the late 1500s that Galileo began to establish some ideas about falling objects. Here is a shot put and a softball. They are about the same size, but the shot put is much heavier than the softball. Now, if someone lets go of the shot put and softball at the same time and from the same height, which will hit the floor first? Stop the tape and write down what you think will happen next to question 1 on your viewer's observation sheet. Here we are, all set to release the shot put and softball. Watch and listen. There, they hit at the same time. Even though the shot put is heavier, they fell at the same speed. It is said that Galileo conducted a similar experiment with 2 cannonballs of different weight. The story says he conducted the experiment from the Leaning Tower of Pisa. That part of the story is probably false, but it is fun to believe that one day Galileo climbed the circular stairs and stepped out on the bell tower balcony. This isn't the real Leaning Tower, but it will lend a feel for what it was like when Galileo let two cannonballs fall. Oh, we won't use cannonballs. The shot put and softball will work fine. Now the shot put and softball are released. There you have it, two objects of different weights landing at the same time. Galileo was right. Objects pick up speed at the same rate. Now let's try something with these two pieces of paper. The papers are identical. We'll crumple this one up and then drop them at the same time from the same height. Which would you expect to land first? Stop the tape and write down an answer for questions 2 and 3 on your observation sheet. Well, the crumpled paper lands first. The other paper sort of floats to the ground. That's because the regular sheet of paper is held up by the air around it. The crumpled paper can move more easily through the air. It has less surface area for the air to hit against. So in this case, the two objects didn't fall at the same speed. It seems to go against Galileo's discovery. Actually, Galileo realized that air can affect the way an object falls. So he said that objects pick up speed at the same rate regardless of weight when gravity is the only force acting on them. When objects fall through air, they may have different speeds. This is because the air resists the fall of objects, and those that are lightest with respect to their size will be most affected. Here is a book and a piece of paper. The book weighs much more than the paper, and when they are let go, the book falls first. But if we put the paper on top of the book so that air pressure under the book can't affect and resist fall of the paper, the two objects fall together. Objects in a vacuum would fall at the same speed. A vacuum is a condition where there is no air or other gases present. Most of the universe is made up of the vacuum of space. One of the astronauts on the Apollo 15 mission to the moon performed an experiment to show that Galileo was correct. The moon has no air. It has no atmosphere. There are no gases around it, so it is in a vacuum. Watch the experiment.
Dan, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
As you can see, the two objects landed at the same time. It showed Galileo was right. When gravity is the only force acting on two objects, those objects, no matter what their weight or mass, will pick up speed at the same rate, or accelerate in the same way. On Earth, we would not get the same results because of air resistance. On Earth, we can create a vacuum with the use of a vacuum pump. The air in this tube is removed. We will release a coin and a scrap of paper. And again they fall at the same speed. Now, if we take this hammer and drop it, will it turn and land with the heavy metal end first? Or will it turn and land with handle first? Or will it simply fall in this position? Stop the tape and answer question 4 on your observation sheet. Watch closely as the hammer is released. If you were thinking about Galileo, you should have guessed correctly that the hammer would fall as held. The heavier metal end has nothing to do with how the hammer will fall. If we flip the hammer, sometimes it will land metal side first, sometimes handle first, and sometimes flat. When objects are falling, it appears they are weightless. If we think of weight as the force an object exerts against the supporting floor, then you can see that an object that is falling seems weightless because there is no supporting floor. A scale falling with the object would register 0, because the scale is falling with the object. 0G, or zero gravity, is what the members of orbiting spacecraft experience while falling around the Earth. Here are some examples. On Skylab, America's first science lab in space, astronauts could run on a track that went in a complete circle. They could do complete flips, twists, and spins. Here is a demonstration of strength as the barbells are lifted out of view. And here, push-ups as never seen before. Two-handed push-ups. Two-person push-ups. Three-person push-ups. One-hand push-ups. And finally, no-hand push-ups. In zero-G environments, there is no up or down, as shuttle crew members sleep in any direction. Notice that when people relax in zero-G, their arms rise. Eating in a weightless environment can be quite unusual. Most people put their pants on one leg at a time. The law of gravity was first introduced by Isaac Newton in the late 1600s. The story is told that he watched an apple fall from a tree and developed the idea of gravity. From that simple, everyday experience, Newton was able to figure out that the same force that made the apple fall kept the moon and planets in their orbits. He said the force of gravity depends on the mass of the objects and their distance from each other. People might argue that the apple falling and the moon's motion are unrelated. However, as Newton stated, the moon is also being pulled by the Earth's gravity and is actually falling around the planet. If the moon were not, it would go sailing off into space in a straight line. So, gravity holds us on Earth and keeps the moon in an orbit around our planet. All the planets of our solar system are kept in orbits around the sun because of the sun's gravity. And many of the planets hold moons in orbit because of gravity. Gravity, then, is more than just the pull towards the center of the Earth. It is found throughout the universe and is common to all objects, large or small. All things have gravity. The strength of gravity is determined by the mass of an object. The greater the mass, the stronger the gravitational attraction that object has. Two objects are attracted to each other, and we speak of the force of gravity. The strength of that force is based on the mass of the objects and their distance from each other. We know the Earth and planets are round, but why? Well, it's because of gravity. The Earth is round because it has attracted itself together as far as it can. There are no corners because every part is almost the same distance from the center of the Earth. This holds true for the Sun and other celestial bodies as well. Today we have taken a close look at gravity. It is an attractive force that acts between any two objects.